Well, it can. And it can because the brain is plastic and modifiable, because it's producing hundreds of thousands of connections a second for the whole of our lives. It's changing the strength of those connections on the basis of what we see, what we hear, what we learn. Let me try and show that graphic in just a couple of examples. This is a remarkable study, actually. I won't try and explain the detail of it, but you can get a feel. This is the study of a large number of twins. Fraternal twins here, that is, twins that are not identical, and genetically identical twins, compared with unrelated pairs of people here. So these are the twins, genetically identical, non-identical twins, and then unrelated people. And each of these columns represents lots and lots of pairs of people whose brains have been compared, and they've all been pulled together. So we're looking at the left-hand side of the brain, the top of the brain here, the right-hand side of the brain, for each of these pairs. And the colors show how similar the thickness of the grey matter of the cortex is in each region of the brain, between the pairs. So the more similar they are, the more red and yellow the areas. So look at this region here. That patch there, on average, amongst these pairs of identical twins, was 30% more, was 30% variation between the twins. Whereas the comparison is the comparison of the unrelated pairs here, which is set at 100%. So much less variation than in unrelated people. So genes are helping to control the structure of brains. That's not surprising. But there's more red and yellow amongst the identical twins than there is amongst the fraternal twins. That's good because, of course, they're more genetically similar. However, even in identical twins, absolutely identical genetically, there are regions of the cerebral hemispheres which are just as different between the twins as this comparable bit of brain for unrelated individuals. So there are large areas of the brain which are apparently not under genetic control, at least for the thickness of the grey matter. And interestingly, they tend to lie outside the regions of primary sensory and motor areas. So these are the parts that have been added by evolution. They're modifiable. They vary in the individual, presumably on the basis of their own experience. So just to give you one example of that, this is a nice experiment done in Oxford, in the imaging centre, in which they asked people who had not played computer games, kids, adolescents who'd not played computer games before. That gets a harder and harder experiment to do. To play Tetris for a few minutes a day for 1 week. They'd never played computer games before. They learned how to play, Tetris, the thing with the falling blocks and so on. Yeah, simple computer game. And they measured the structure of the brain, every detail, the size of every layer and thickness and region of the brain before the week and at the end of the week. And the region, here are the brains, averaged over this group of subjects, and any area which is not just grey, any area with any colour has changed. It's changed its thickness of the grey matter simply as a result of playing for a few minutes each day, playing a computer game. So Willis was right. Brains can literally grow and change as a result of how they're used. And this is a pretty crude way of measuring the change. What matters is these changes presumably reflect computationally important changes in the strengths and the wiring of the nerve cells in each of these regions, which are changing the way that they function. So I'll skip, I think, this slide. It's just another example of change. I'll just leave you with a series of images to show the developments in our cultural history from the very beginning of cuneiform script through progressively over several hundreds, thousands of years to the kinds of things that we are now doing, all with a Stone Age brain. I think it's reasonable to say that everything that human beings are doing differently now compared with what they were doing 200,000 years ago are unlikely to be due directly to genetics and genetic change. And they're due to the plasticity of the brain, the things that are learnt by individuals in each generation, which are passed on to others through education, through parenting, through training and learning, through reading and writing, to the next generation, on and on and up. We're climbing on the shoulders of previous generations by learning what they learnt, inheriting their knowledge, and moving on from it, not on the basis of genetic change. This is all very, well, that's good news and bad news. The good news is the shape of that function that Stephen Oppenheimer grew. It's rising exponentially. There's no reason to believe that our capacity to reinvent ourselves, to move on and up, is decreasing. Just the opposite. Contrast, this environment to 500 years ago. We're completely different and phenotypically completely different organisms, simply on the basis of our own ability to learn. So there's hope for the future despite all the challenges. That's what I'm saying, because we have that kind of brain that appears to have, not unlimited resources, of course, but doesn't look as though we've reached the limit. However, the bad news is that it's not Darwinian. Therefore, it's not stable. It's not based on something which is simply automatically inherited through sexual reproduction. It's based on the tedious and difficult task of teaching and learning. It's a sobering thought that a single generation without books, without the internet, without schools, without universities, say we just lost it for one generation, we will be back in the Stone Age. I mean, literally identical to those early hominids from 200,000 years ago, beginning the whole story again. So there's a good part of the story and a bad part of the story, but I hope I've convinced you that perhaps the most important and distinctive part of human beings can't be explained simply by Darwinian natural selection. Thank you.